In section 2.8, we're going to look at arithmetic operations on functions, the difference quotient, and the composition of functions and their domain. Given two functions, f and g, then for all values of x for which both f of x and g of x are defined, the functions f plus g, f minus g, f times g, and f over g are defined as follows. F plus g of x is the sum of two functions, f of x plus g of x. F minus g of x is just the difference of two functions, f of x minus g of x. F times g of x is equal to f of x times g of x. And finally, f divided by g of x is equal to f of x over g of x. Here, the denominator cannot be equal to 0, or it will be undefined. For functions f and g, the domains of f plus g, f minus g, and f times g include all real numbers in the intersection of the domains of f and g, while the domain of f divided by g includes those real numbers in the intersection of the domains of f and g, except when g of x is equal to 0 or when the denominator is equal to 0. Example 1, let f of x be equal to x squared plus 1 and g of x is equal to 3x plus 5. Find each of the following. Part A, let's look for f plus g of 1. Let f of x be equal to x squared plus 1 and g of x be equal to 3x plus 5. Find each of the following. F plus g of 1. So in part A, I want to substitute a 1 into f plus g and figure out what that value is. We'll start with the definition. F plus g of x means f of x plus g of x. So to do f of 1, we'll plug in f of 1, figure out what that value is, and then add g of 1. So let's simplify f of 1. F of 1 means plug in 1 into the function f. So we have 1 squared plus 1. And g of 1 means plug in 1 into the x of g of x. 3 times 1 plus 5. And then we'll simplify our expression. 1 squared gives us 1. 3 times 1 gives us 3. And we bring down the 5. Let's collect like terms. 1 plus 1 plus 3 plus 5 yields 10. Part B, we want to find f minus g of negative 3 with the same functions as earlier. We'll start with the definition. F minus g of x is equal to f of x minus g of x. So in this problem, we're going to plug in a negative 3 into both f and g. F of negative 3 minus g of negative 3. F of negative 3 means substitute negative 3 into the function f. So we have negative 3 squared plus 1. We're going to subtract. I'm going to be extra careful with the g function. So I'm going to put a set of brackets so I can distribute that negative throughout the expression for g of negative 3. We have 3 times negative 3 plus 5. Here we substituted that negative 3 into the x for the g function, and then we'll evaluate the right side first. Negative 3 squared plus 1 minus, and inside the brackets we'll do 3 times negative 3, which is negative 9 plus 5. Again, we'll simplify the brackets first. Negative 3 squared plus 1 minus negative 5 plus 9 is negative 4. Then we'll do the parentheses. Negative 3 squared is equivalent to 9. 9 plus 1. And we have the double negative here. We'll just make that a plus 4. And finally, our solution is 14. Part C, let's find f times g of 5. According to the definition, f times g of x is equivalent to f of x times g of x. So for part C, we have f of 5 times g of 5. We'll plug in the 5 for the function f. So this becomes 5 squared plus 1. And then we're going to multiply that with g of 5. So we're going to substitute 5 into the g function. 3 times 5 plus 5. We'll simplify 5 squared plus 1. That results in 25 plus 1. And 3 times 5 is 15. And we'll add 5 later. This reduces to 26 times 20. And our final solution is 520. Part D, we're doing a quotient, f divided by g of 0. We'll start with the definition again. F over g of x is equivalent to f of x divided by g of x. According to the definition, part D implies f of 0 divided by g of 0. We'll plug in a 0 into f, and that gives us 0 squared plus 1 divided by, we'll plug in a 0 for g, and that gives us 3 times 0 plus 5. We'll simplify the numerator. 0 squared plus 1 is just 1. And in the denominator, 3 times 0 plus 5 is 5. So f over g of 0 is 1 over 5. Let f of x be equal to 8x minus 9 and g of x be equal to the square root of 2x minus 1. Find each function. Part A, we want to find f plus g of x. We'll use the definition. This is equivalent to f of x plus g of x. And that means we'll take the function f of x and we'll add that to the function g of x. That results in 8x minus 9 plus the square root of 2x minus 1. We'll try to simplify if possible. And in this case, this is simplified, so we're done with the problem. Part B, we're doing f minus g of x. From the definition, this is equivalent to f of x minus g of x. So we'll take the function f of x, and we'll subtract it from the function g of x. F of x is 8x minus 9, and we're going to subtract the square root of 2x minus 1. In the problem, we have there's a negative symbol, and we're going to multiply that to the square root, which just simplifies to 8x minus 9 minus the square root of 2x minus 1. Part C, we're going to multiply the two functions. F times g of x is equivalent to f of x times g of x. So we'll multiply 8x minus 9 times the function g of x, which is the square root of 2x minus 1. And that completes the problem. Even if we distribute the 8x and the negative 9, it would not simplify this problem, so we are done. Part D, let's find f divided by g of x. By definition, this is f of x over g of x. And we'll take the function f of x and put it on top. That's 8x minus 9. And we're going to divide that by the square root of 2x minus 1. So this is our quotient function. In part E, we want to find the domains of the functions we did in parts A through part D. To find the domains of the functions, we first find the domains of f and g. The domain of f is the set of all real numbers from negative infinity to infinity. Notice for the function f of x, we have it's a line, it's defined everywhere, and we can plug anything we want for the x value, so the domain is from negative infinity to infinity. Because g is defined by a square root radical, the radicand must be non-negative, that is greater than or equal to 0. G of x is a square root function, so it's defined everywhere except when the number on the inside, the radicand, is negative. It is defined everywhere unless the radicand is negative. We know that f of x is defined everywhere, so we'll focus our attention on g of x, which is only defined when the radical is greater than or equal to 0. So I'll set 2x minus 1 greater than or equal to 0, and we'll solve for x. Add 1 to both sides. 2x is greater than or equal to 1. Divide both sides by 2, and x is greater than or equal to 1/2 now. That means our domain for g of x is going to be from 1/2 to infinity. F of x is defined from negative infinity to infinity, and we know g of x is defined from 1/2 to infinity. So the domain of all our functions, f plus g, f minus g, and f times g, must be defined for the intersection, negative infinity to infinity, intersection with 1/2 to infinity. And the intersection between these two intervals is just 1/2 to infinity. So this is now the domain of our functions. To find the domain of f divided by g of x, we're going to look for all the values that will cause the denominator to be undefined. G of x cannot be equal to 0, as it would cause our function to be undefined. So we'll take the square root of 2x minus 1, and we will not allow it to be equal to 0. We can square both sides, and that results in 2x minus 1 cannot be equal to 0. Add 1 to both sides. 2x cannot be equal to 1, and finally x cannot be equal to 1/2. Recall the domain of f of x was from negative infinity to infinity. The domain of g of x is equivalent to 1/2 to infinity. But remember, we cannot have a value of 1/2 because that would cause g of x to be equal to 0. So the domain of f divided by g of x has to not include 1/2, but be the intersection of f and g. So their intersection excluding x equals 1/2 is equivalent to a parentheses 1/2 comma infinity. We cannot include the 1/2, so we'll put a parentheses around it. So this is the domain of f over g of x.